Welcome. Today we are going to start with droplet combustion. So, we have studied vaporization, we have studied atomization, and now we are going to study the droplet combustion part. And as you will find that the droplet combustion is very similar to the droplet vaporization, okay, except now that instead of the ambient you now have a flame that surrounds it. Okay. So, if you look at the PPT, there are certain, and some of these are work taken from multiple sources. I will give you the references. Many of this work are done by Professor Tom Abedisian of Cornell University. So, what happens is that you will see that if you look at it closely, okay, there is a flame front that actually surrounds the droplets. If you look at this, there is a flame, this is a flame, right. So, it is a droplet and then there is a flame around it. If it is a round flame, it is under microgravity condition. If it is a flame like this, then this is under the normal buoyant flame that you will have around a droplet, right. And the droplets, basically why droplet combustion is important, because the droplets represent the subgrid structure of a spray. Okay. The spray is actually millions of droplets. Okay. So, in the sprays the ignition happens, that means the fuel has to be ignited in the multiphase region, right. So, if you once again look that here, for example, there is a spray that is coming out which contains millions of droplets. This is ignited right over there, right, and then you get this flame structure. If you look closely at the flame, that means if you take a region, zoom out from that region, you will find that there are multiple droplets with an encompassing flame around it, like that. Now, if it is a very less dense spray, right, dilute spray, you will find that the droplets are further apart and you get separate flames around the droplets. Okay. Like for example, here or here, something like separated flames that you get. In many cases you can get a composite flame also. This depends on the separation distance between the droplets. So, dilute spray means that the droplets are well separated. That means L by D is basically approaches infinity, where L is the separation distance, D is basically the diameter of each of the droplet. Okay. So, the droplet combustion basically means that there is a droplet and then there is a flame. So, if you look at this particular graph, this will be very clear. So, we will first do that Dsquare law for corresponding to droplet combustion. So, what you see over here is basically this is a nice and round droplet, right. There is a flame front which sits around it, around the droplet over here, you can see it, right. Okay. So, there is evaporation of the droplet is basically fuel droplet. Okay. So, it can be any fuel. Okay. This fuel vapor, and it is a single component droplet, that means one single component of fuel is present. This fuel vaporizes, gets diffused to the droplet, to the flame surface, right, where the flame front is established, right. The flame actually gives out heat in both the directions. This heat goes towards heating the ambient or the oxidizer. This heat actually goes to the droplet and aids in the vaporization process. Okay. So, this flux of heat which comes from the flame into the droplet is like heating the droplet from the ambient. This situation is equivalent if you put the droplet in a heated flow essentially, right. Okay. But the heat that goes towards the air side, okay, or the oxidizer side is very important, because the air also needs to be oxidized, the temperature needs to be brought up for flame or a reaction to be established, right. So, this is called the outer diffusive convective region, this is the inner diffusive convective region, this is the reaction sheet of the flame front, this is the ambience, this is the oxidizer gas which approaches the flame front, and this is the fuel vapor which also approaches the flame front from the two opposite directions, right. So, if you look at this flame front very carefully, so this is the flame front that we have. Okay. This is some interesting things that you will observe over here. One particular case is that YFS is basically the concentration of the fuel vapor near the droplet surface, right. What happens is that this fuel vapor concentration, okay, as you go towards the interface, it slowly decreases. That is because here it becomes absolutely equal to 0, because the fuel vapor is completely eaten up by the flame front, right. Similar thing you see for the oxidizer. At the far field, the oxidizer has got some concentration which is Y0 infinity. Oxidizer concentration also comes down and gets depleted over here, right. So, at the flame front, both the oxidizer and the fuel gets eaten up. Okay. that is the beauty, right. So, you have the flame the YF decreasing, this Y0 also decreases, right. One other thing you have, this is the temperature at the droplet surface which is given by Ts. Ts also increases and goes to some flame temperature Tf. Okay. This Tf, the flame temperature, is nothing but the adiabatic flame temperature for stoichiometric concentrations, right. If you do not recall stoichiometry and other things, please pick up your combustion, very preliminary course on combustion, and you can read it. Air temperature also increases, okay, at the flame front. So, at the flame front, both the oxidizer and the fuel actually has the temperature Tf, that is the flame temperature, right. The droplet surface temperature is much lower than the flame temperature. Remember this, when there is a burning droplet, do not think that the droplet surface temperature is as high as the flame temperature, that is wrong, right. The droplet surface temperature is at some temperature Ts, which is mostly like the wet bulb limit. In most cases it is the boiling point temperature of the fuel concerned, right. Air temperature far field is the normal air temperature, that is far away from the droplet, but it slowly gets heated and it goes to the flame temperature as it approaches the flame. So, now you can see where this heat goes. Part of this heat goes towards heating the oxidizer, part of the heat goes towards heating the fuel and evaporating it, right. So, what happens is that the heat from the flame, right, it serves varieties of purpose, right. First and foremost, what does it do? It first heats oxidizer, right, it first heats the oxidizer, right. It also heats the fuel, right, plus it aids in the gasification. Gasification is basically nothing but evaporation, got it. So, that is the purpose of the heat source, got it. And this is a spherically symmetric process usually, okay. The gasification mechanism is basically the same as droplet vaporization. The droplet does not know what it is, where the heat is coming from, except that the heat source is now the flame than the ambience, because the flame is a heat release source, there is a chemical reaction that is going on. The flame also serves as a sink for the outwardly transported fuel and the inwardly transported oxidizer gas. So, it basically eats up both the fuel and the oxidizer, okay, if they are coming in stoichiometric proportions, got it. So, that is the basic premise how the flame is established. Of course, this flame does not include the effect of buoyancy or any other things, okay. In most of the cases when you have situations like that, there will be the flame that will be created where there will be a lot of buoyancy driven effect, right. The flame will be a flame in which the flame will be like this, it will be like a teardrop, okay, instead of a flame like this. Okay. So, this is now vitally important now that you understand that how does the droplet combustion actually takes place. So, there is a flame, slowly the reactants or the fuel in this case diffuses to the flame front, oxidizer also comes diffusing from the outer from the ambience to the flame front, okay. There they react and the reaction is actually established, okay. Now, you can see that the flame here we have taken that there is no leakage. So, this flame, across the flame there is no leakage of oxidizer or fuel, okay. So, it is like a perfect sink. So, this is a flame. So, if you look at it, it's like a flame like this. Usually the flames are thick. If you look at the have the PPT, what will happen is that the oxidizer gets diffuses to the thing, the reactants also gets diffuses to the flame front. Now, in the flame front, if you look at the flame front, there is no leakage, that means the oxidizer does not go to the other side, the reactants does not come to this side. So, the flame is up like a perfect curtain, it does not allow, it is like a perfect filter, okay. So, that is the basic, but in most of the cases they do leak, okay. So, there is those are basically different issues, and also we have not taken into account any accumulation that actually happens in that inner region. If you look at the PPT, this inner region is a region here, okay. So, let us write now the governing equations for the same, and let us see. So, let me go to the journal and write the governing equations for the flame, okay. So, basically we start with the continuity, okay. So, the continuity, from the continuity you basically get the burning rate, burning rate of the flame. Okay. So, the burning rate of the flame will be actually interesting. So, the burning rate. So, the burning rate of the flame is given as mc 4 pi r square into rho u. U is basically the radial velocity. We will go a little fast because you already have seen some of these equations earlier in different forms. Okay. So, that is the radial velocity, that is usually comes because of the Stefan's flow, right, because of the gasification. Okay. That if you recall, that was the Stefan's flow. Okay. Now, we introduce something called a coupling function. Now, what is a coupling function over here? The coupling function is beta I into yi. Okay. So, that is the coupling function. If you do not recall it, just read your combustion materials. Okay. You will know that what is this coupling function, what is Swab-Zaldovich variable and things like that. Okay. So, we do a conservation of the coupling function. This is useful. Okay. So, the conservation of the coupling function. So, once we do the conservation of the coupling function, this is basically lambda by Cp r square to 0. Here I is basically can be oxidizer, it can be the fuel. Okay. So, that is the thing. Okay. We are assuming that this lambda by Cp is basically a constant. Okay. And we are also defining this m dot c as mc divided by 4 pi lambda by Cp into Rs, where Rs is basically the droplet diameter or the surface. Okay. So, you got it. So, using the non-dimensional variables, okay, using the non-dimensional variables where r tilde, you can define it as r by Rs also. So, if we can write d by dr mc tilde beta I minus r bar square d beta I by d r tilde is equal to 0, where once again your I is equal to 0 and is O and F, basically the oxidizer and the fuel combined. So, this is the equation that you get using the coupling function. Do not be too much bothered once again about the math. This is a very simple equation that we have written, okay, and this is basically the burning rate. Okay. So, the burning rate has been normalized, okay, and we have just used the normalized variables for the next few things. Okay. Now, if we go to the first, if we evaluate the first and second integrals, okay, okay. So, that is what you get, that is the first one, and then this is the second one. If you integrate it one more time, okay. So, that is the second integral that you are actually going to get out of this. Okay. So, how to now the problem remains that how to find out this integration constants, right. So, there are two integration constants, this and this, these are the two integration constants. Okay, integration constants. So, the integration constants can be evaluated by applying the boundary conditions. So, applying boundary conditions. So, what will be the boundary conditions? The boundary conditions will be as r prime goes to infinity, y 0 goes to y 0. This is the oxidizer that will go to the infinity of its own, right, its own concentration, that is the ambience. The fuel will be 0 and the temperature will be the same as T infinity, right. Even without the non-dimensional symbols you can make out, right. The temperature should go to the temperature ambient, right. The concentration of the fuel vapor will be actually equal to 0 far away from the droplet, and the concentration of the oxidizer will be whatever its initial concentration was in the ambient, like the normal ambient, right. Okay. However, at R bar equal to 1, that is on at the droplet surface, the things are a little bit more complicated. Equal to 0, that is condition 1, and we will look at what these things exactly means. This is 1, this is 2, and there will be one more that we are going to write over here. QV and T tilde is equal to Ts. This is like 3 and this is like 4. Got it? So, these are like 4 equations that the 4 boundary conditions. Now, we are going to look at the stature of each of these equations in a little bit, okay, and the non-dimensional parameters can be like this is YF by YF naught, okay. QV is basically nothing but QV divided by QC. QC is the heat of combustion, okay, and Y naught is basically Y naught by the stoichiometric coefficient, right, that is sigma naught, okay. Once again, if you do not know all this stoichiometric coefficient and other things, please read up your combustion book, okay. So, let us look at the boundary conditions in kind of details. For boundary condition 1 that we covered over there, this essentially means that the net oxidizer transport vanishes, okay, at the interface. So, net oxidizer transport, okay, the physical meaning vanishes at the interface. Interface is basically the liquid, that is the droplet surface, okay. There is no penetration of oxidizer into the liquid phase. Got it? Okay, so that is the first thing that we should know. The second, so this equation was this equation, this particular equation that we had, right. This can be also written in a compact Dirac delta type of notation, but for the sake. So, net fuel transport is nothing but is the same as fuel gasification. Okay, that is also given over here. This is this expression that you see. On the right hand side you see the gasification or MC tilde, right. So, that is what it actually implies. Okay. The third is basically, the third actually tells you that the heat conduction okay, from the flame is used for gasification. That is about it, right. Okay. So, these are the, so what we have now this equation which has got 2 constants of integration, these boundary conditions, right. Using all of these things together, that means solving, we basically get beta oxygen, that is the coupling function, Ts tilde, QV tilde you already know what these QVs are, T infinity tilde Ts minus QV tilde that is the first expression. Similarly, for fuel you can write another one, okay. So, these are the two expressions. By solving this you get these two expressions over there, right. Okay. Now, we need to determine MC, the flame standoff distance, and TF, the flame temperature. These are the three parameters that one needs to establish. The flame standoff distance you already know. What is the flame standoff distance? If you do not know, just take a quick look at the, so this was the flame standoff distance from here to here, that is the flame standoff distance, right, that is RF, okay. That was the flame standoff distance, okay. So, and so this is the thing. Now we can write down the reaction sheet requirements. This was all written from a droplet surface perspective, right. Now we let us write the expressions for the reaction sheet requirements. So, the reaction sheet requires, okay, number 1, Y naught at the reaction sheet is basically equal to 0, right, because at the sheet the oxidizer concentration should be equal to 0. 2, YF at the reaction sheet is also equal to 0. That is also makes sense because the reaction sheet, as we say, it is a perfect sink for both the terms, right. Y naught at 1, okay, that is equal to 0, that is, this is at the droplet surface. Why this is equal to 0? Because there is no leakage, we already said, right, no leakage of oxidizer across the reaction sheet. There is no leakage of any oxidizer across the reaction sheet, that is very, very important, right. So, from these expressions we can first write MC is equal to ln 1 plus BHC. Now, remember this heat transfer number that we have written is for combustion, it is the Spalding heat transfer number for the combustion, okay. So, heat transfer number for combustion, right, it is a heat transfer number for combustion, got it, okay. So, similarly the RF is given by MC into ln 1 plus this can be also written as ln 1 plus TF minus TS divided by QV divided by, if you solve, we are once again not going through all the math, we are just showing the basic steps. So, that is RF, the QC, which is the combustion heat, this is the dimensional form, Tf minus T infinity, this is sigma naught plus 1 minus 0 by 0 infinity into sigma naught, okay. And lastly the heat transfer number is basically Cp into C infinity minus Cs, okay, plus y 0 infinity by sigma naught into Qc divided by QV. Got it? Okay. Now, if you look at these expressions, say for example, so we have found out what is the expression for the combustion rate, or rather the gasification rate. This is the flame standoff distance where the flame will stand, and this is the corresponding heat release of the flame, right, and this is the corresponding Spaulding or the heat transfer number. Just look at one thing, if we just deal with pure vaporization, what will happen is that this term, if you look at the expression over here, y0, this particular term will actually have no significance, right, will have no significance. As a result of that, if this is equal to 0, right, this will boil down, this BHC will boil down to the pure vaporization case, right. All these expressions will boil down to the pure vaporization case. You can look at it and you can see that why that should be the case. Let us take the first expression. If you look at the first expression, this expression boils down to the pure vaporization case, because BCH will be the same as the pure vaporization Spaulding heat transfer number, right. RF becomes non-existent in this particular case, and QC becomes the same as QV plus this additional heat. Okay. And of course, TF in this case does not make any sense, so this also goes. So, QC becomes the same as QV in this case. Okay. So, this has got some additional significance if you look at it. Okay. So, that what is the significance of QC? QC is the heat release per unit mass of fuel, and this is equal to the amount of heat needed to gasify the fuel plus heat it from Ts to Tf, that is the flame front, plus the amount of heat needed to heat oxidizer and inert gas from ambient, that is T infinity to Tf. So, that is the role of heat release, right. If we make y0 infinity is equal to 0, we recover the pure vaporization equations, right. That should be what it is, right. Ts is almost like the boiling point temperature, that is the boiling of the fuel, boiling point of fuel. Okay. And so, these are the generalized set of equations that we have in this particular exercise, right. Now, in order to derive the D-square law form, okay, what we can do is that we have to equate for D-square law. What we need to do is that we say that mv is equal to mc, that means the vaporization is the same as the gasification. This has got the implication that there is no accumulation of fuel, right. So, whatever is being produced is actually the fuel, that is actually instantaneous rate of fuel gasification is equal to the rate of the fuel consumption, okay, at the reaction sheet. So, mv is the same as your mc. So, mc is basically what, 4 pi lambda by Cp into Rs into ln into 1 plus Bhc, right, that we just now said, that is what it is going to be. Remember that previous expression was for m tilde. So, if you just dimensionalize once again, that is the form that you are going to get. Now, the rest of the thing becomes very easy. When you have a form like this, okay, mv on the other hand is given by the rate of change of droplet diameter, which is like 4/3 pi Rs cube divided by into rho L, right, that is mv, right. So, what we have said that the fuel gasification is the same as fuel consumption. That was the basic assumption, right? Consumption at flame front. Got it? Okay. So, now if you just equate this expression with the previous one that we wrote for MC, this will give you the same dRs square by dt equal to minus Kc. Kc is equal to 2 lambda by Cp by rho L ln 1 plus Bhc, right. This you can recall, this is the modified heat transfer number, HTN. Okay. So, usually this is the burning rate and it is constant. Okay. And we also have Rs at t equal to 0 is equal to Rs 0. So, based on these two expressions, if we integrate it, you get Rs square equal to Rs 0 square minus Kct, right. Okay. Kct, that looks exactly like the d-square law, right. So, if you divide Rs square by Rs 0 square, it will be 1 minus Kc by Rs 0 square into t, right. So, that is the d-square law, right, equivalent of the d-square law, except k has been replaced by Kc over here, right, and the total combustion time is tau c is equal to Rs 0 square divided by Kc, right. So, these are the two expressions that you get after all these things. So, what we have got here? We have got the flame standoff distance, flame temperature, the revised heat transfer number, the chemical heat release rate, and from that we have shown that it can be also shown that the droplet combustion also follows the similar d-square law with whatever assumptions that we made in the d-square law, right. And we also showed that if you just turn on the oxidizer concentration to be equal to 0, you recover the original vaporization equation. Okay. So, in the next class we are going to complete this discussion on droplet vaporization, and we are going to look at after that we are going to look at some more phenomena related to this, how the droplets burn, how they burn as a cluster and things like that. Okay. So, but these are the mathematics which you might want to just do a brief review. And once again TF, just I want to write it down over here, TF is nothing but the stoichiometric adiabatic flame temperature. Okay. So, we end the lecture here. In the next lecture we are going to pick up and see that what other things we can learn about this droplet combustion. Thank you.